So a 51.8 kilogram bungee jumper jumps off a bridge and undergoes simple harmonic motion. If the period of oscillation, so its period is 11.2 seconds, what is the spring constant K? And mass of the bungee jumper is 51.8 kilogram. So the time period of the oscillation is given by 2 pi m over k. So we can, in order to find k, we can square on both sides. Then we get t squared is 4 pi squared. Squaring the square root will cancel that square root. So then we'll have m is 51.8 kilogram over k. Okay, so we want to find k. So multiply both sides by k, you get t squared k is 4 pi squared times 51.8 kilogram, and then divide both sides by t squared. Cancel t squared and t squared, so k is 4 pi squared, 51.8 kilogram, and then t is 11.2 seconds. Okay, that's squared. So calculate that. That will give you k. K is measured in Newton per meter. Now let's look at another problem. So a simple harmonic motion oscillates with frequency f when its amplitude is a. If the amplitude is now double to 2a, what is new frequency? This is a conceptual question. Amplitude does not affect the frequency. So that means even if you double the amplitude, the frequency will still be f. Okay. So we have a 0.415 kilogram mass suspended from a spring, undergoes simple harmonic motion with period of that. How much mass in kilogram must be added to the object to change the period to 1.75? So you have a spring mass system. Okay, for this mass of m1, the period is 1.25. Now you added some mass on it. Okay, this is now a little bit heavier, so that's called m2, where m2 is m1 plus some additional mass. So for that, time period is now 1.75 second. So we want to find the additional mass, which is m2 minus m1. Okay, so for the first one, we can write t1 is equal to 2 pi m1 over k. The spring is same, so it doesn't say we are using different springs, so we can just use same time spring constant k. So for t2, it's 2 pi m2 over k. So we can divide the two equations term by term. So t1 over t2. We want to find m2, so let's divide t2 by t1, second equation by the first equation. So t2 over t1 is equal to 2 pi m2 over k. 2 pi, that term is m1 over k. So let's take the square on both sides. So t2 over t1 square, 2 pi and 2 pi cancel. So square root of m2 over k, square root of m1 over k square. So this square and the square roots cancel. So m2 over k, m1 over k. So k and k cancel. So we have m2 over m1. So we want to find m2. So m2 would be m1, multiply both sides by m1. So you get m2 is m1 times t2 over t1 squared. Okay, and then you can substitute the given values. So m1 is 0.415 kilogram, and then T2 is 1.75 second, and T1 is 1.25 second square, so that will give you M2 kilogram. And then to find the additional mass, which is delta M, the mass you need to add to change the time period to 1.75 seconds, that would be M2 minus M1. Okay. A diver on a diving board is undergoing simple harmonic motion. So that's the diving board. Okay, it's going simple harmonic motion. Our mass is 51.5 kilogram, and the time period of oscillation is 0.75 second. And on the same board, okay, another diver undergoes simple harmonic motion, but for this person, let's say his mass is M2, which is unknown. The time period is 1.015 second. Okay, so what is the mass of this person? It's exactly the same kind of problem like we did in the previous one. So T1 is 2 pi M1 over K, and T2 is 2 pi M2 over K. So divide equation 2 by equation 1. So T2 over T1 is equal to 2 pi M2 over K over 2 pi M1 over K. Okay, so square both sides. You can cancel 2 pi and 2 pi, so we have T2 over T1 squared. That's equal to M2K over M1K. Okay, we are cancelling the square roots and the square. So can K cancel? So M2 dividing multiplying both sides by M1, we get rid of this M1. So that will give us T2 over T1 squared times M1. So T2 is 1.015 second, T1 is 0.75 second. That's squared, and the mass of the first person is 51.5 kilogram. Okay, and do the math, you will get the mass of the second person. So let's look at another question. Near the top of the Citigroup Center building in New York City, there is an object with mass of 3.2 times 10 to the 5th kilogram on springs that have adjustable force constants. Its function is to dampen wind-driven oscillations of the building by oscillating at the same frequency as the building is being driven. The driving force is transferred to the object, which oscillates instead of entire building. What effective force constant should the spring have to make the oscillation with a time period of 1.2 seconds in Newton per meter? What energy is stored in the spring for 1.2 meter displacement from its equilibrium? Okay. So this is pretty straightforward if you know the equation. So we want to find the effective force constant. So force constant here means the spring constant. Okay, it's K. To find the K. The time period again is 2 pi mass over K. We want to find K, so you can take square on both sides. So 4 pi squared M over K, and then multiply both sides by K. So K and K. So you can cancel K and K. And then also divide both sides by T squared, just to get rid of that on the left. So then K would be 4 pi squared m over t squared. Okay. So 4 pi squared, mass is 3.2 times 10 to 5th kilogram over time period is 1.2 second squared. Okay, so you do the math, that will give you the spring constant in Newton per meter. And then what is the energy stored? So we know from our previous chapter, the spring stores potential energy, which is given by this formula. So potential energy of a spring, either compressed or stretched spring, is 1/2 k delta x squared. So 1/2 k is whatever you find from here, that's k, and delta x is the stretching or compressing of the spring. So in this case, the spring is compressed by 1.2 meter. Okay, that's squared. So that'll give you potential energy in joules. Let's look at another question. A 75 kilogram person is bouncing on a bathroom scale which has a force constant of 1.25 times 10 to 6th Newton per meter. What is the maximum velocity of the person in meters per second if the amplitude of the bounce is 0.115 centimeters? And what is the maximum energy in joules stored in the spring? So we want to find the maximum velocity. So what we need to do here is to find the maximum velocity. Okay, so that's the spring of the scale, and it's bouncing up and down. It's compressed and then it's extended. So here, to find the maximum velocity, we want to use conservation of energy. So when the spring is at the maximum displacement position, its displacement would be amplitude. Okay, so that's the equilibrium. So it's stretched, it goes up to here. So this is the amplitude, the maximum displacement. And during the stretching, its energy during maximum amplitude, that would be equal to energy at any other instant. Again, like I said before, no matter where the spring is or what the configuration of spring is, its total energy is always same because energy is conserved. Okay? So whether it's stretched like that or whether it's compressed like that or whether it's in equilibrium, it's always same. So that means we know the energy in the stretched condition, this maximum stretched condition, is only that of the potential energy. There is no kinetic energy because at the maximum displacement it momentarily stops, so there's no speed at that instant, so there's only potential energy. So this is only potential energy. So potential energy is K extension delta x. In this case delta x is A, so A squared. And at other instances it's the combination of kinetic energy and potential energy. Okay. Now kinetic energy is 1/2 mv squared and potential energy is 1/2 k delta x squared. Okay. So we can cancel half and half. So we want to find V, so let's write this equation in terms of V. So we have Ka squared here, take this to the left, so that would be K delta x squared, that is equal to mv squared. So K and K common, you can take outside the parentheses, so A squared minus delta x squared, that is equal to mv squared. And then this m, divide both sides by m, you get K over m. Okay, A squared minus, this is the displacement, and for simple harmonic motion, displacement is given by this formula, A cosine or sine omega t plus phi. Suppose we don't care about that. So this is basically tells us where the this curve starts. If it starts from 0 point, then this phi is just 0. Okay. If it doesn't start from 0, like it starts from, let's say, a little bit before 0 or a little bit after 0, like that. Then in this case, this phi is this distance, okay, where it starts. But let's assume that in this case the curve starts from 0 position of this sine wave. So this is the displacement, okay, and this y is basically when it's the vertical displacement, when it's moving up and down. But in some cases the spring may also be moving back and forth like that, okay, right and left. In that case, instead of y, we just write x. So x a sine omega t. Okay, so we can replace our delta x by that a sine omega t. So a delta x squared, okay, is a squared sine squared omega t is equal to m. We already got rid of m, divided both sides by m. So that's v squared. So k over m, as squared and a squared are common, so pull it out. So 1 minus sine omega t, sine squared omega t is v squared, k over m, a squared. So 1 minus sine squared theta is cosine squared theta, okay, cosine squared omega t. Now let's take square root on both sides. So that's square root and square cancel, this square and square root cancel, and that cancel. So we get v is equal to a k over m cosine omega t. And I showed in the very beginning that this thing k over m is omega. Omega is k over m. So this is the expression of velocity at any point, okay, or speed at any point during the simple harmonic motion. It's given by a omega cosine omega t. But now we want to find the maximum velocity, okay, so here we are looking for maximum velocity, and we get the velocity to be maximum when this cosine omega t is 1, okay. I mean, cosine omega t can have any value between 0 to 1, and this won't give us the maximum value, or anything in between won't give us the maximum value. But we have, if we have cosine omega t to be 1, then that would be the maximum value. So v max would be a omega, okay. So we want to find that. Again, a omega is again k over m, okay, k over m. So let's plug in the numbers. So v max is, so let's see, we have a is 1.115 centimeters, so centimeters is 10 to negative 2 meters, and then square root k, force constant, is 1.25 times 10 to 6 Newton per meter, over mass is 75 kilogram. Okay, so when you do the math, you get the maximum velocity. Okay, and then the next one is, what's the maximum energy stored in the spring? So energy stored in the spring is given by this formula 1/2 k delta x squared, and maximum energy would be when the spring has the maximum amplitude, or maximum displacement, which is the amplitude. So let's say this is the equilibrium. So when you stretch it, it will have more and more potential energy, and at the maximum displacement it will have the maximum potential energy. No kinetic energy, just the potential energy, and the distance corresponding to that is the amplitude, okay. So here this thing would be this would be a maximum displacement. So potential energy max is 1/2 k a squared. So 1/2 k is 1.25 times 10 to 6 Newton per meter, and then a is 0.115 times 10 to negative 2 meters squared, okay. So So that'll give you potential energy in joules. Okay, that's all for this lecture. You should be able to do all the homework problems with this concept. If you guys have any question, please feel free to email me. Okay, let me know. I would be more than happy to help.